Welcome back. In my previous video, I had seen what is series and what is convergence and divergence of series. What is series of function? This I have discussed in my previous video elaborately. Today I will discuss at first some tests of convergence and divergence of series. Because actually today's goal of this lecture is power series. What is the power series? This is actually a new concept, but at first as a review, I will discuss some test of series about convergence and divergence. Okay, what is the power series? What is the radius of convergence? This is actually goal of this lecture. At first, let's see some example of the series to define power series in better way. First test is alternating series test. We all of us know this type of series. This is look like series n equal to 1 to infinity minus 1 to the power n plus 1 an. And if absolute value of an convergent, when absolute value of an convergent, then we can tell the series is convergent absolutely. All of us know there are many examples, those series which is convergent conditionally by Leibniz test we can tell, but this series does not converge absolutely. Now I will say this type of example. Our first example, in my previous video, I had seen this series is convergent by Leibniz test, but not absolutely convergent series. Today I will see this type of example, which is convergent by Leibniz test, but not absolutely convergent. Such type of example I will see. First example, now I will see the series n equal to 1 to infinity minus 1 to the power n sine 1 over n. Here n equal to sine 1 over n, and we all of us know graph of the sine x in the interval 0 to pi over 2, such type. And since here's 1 over n, we all of us know this is 1 over n always less than 1. If consider this is less than pi over 2, because pi over 2 means 1.57. In this interval, sine 1 over n always would be decreasing. The sequence an, which is sine 1 over n, is decreasing sequence in this interval 0 to pi over 2, because sine x always lies between 0 to 1, and limit n tends to infinity sine 1 over n equal to 0. Since the sequence an is decreasing sequence and limit n tends to infinity an equal to 0, therefore by Leibniz test we can tell the series n equal to 1 to infinity minus 1 to the power n sine 1 over n is convergent. By Leibniz test. But this series not absolutely convergent, because absolute value of an equal to sine 1 over n. Now apply limit comparison test. Limit n tends to infinity sine 1 over n over 1 over n. We all of us know this value is 1. And since the series 1 over n equal to 1 to infinity, this series is divergent series. Therefore, limit comparison test, we can tell the series sine 1 over n is divergent series. And since the series is divergent series, therefore our given series is not absolutely convergent series. Okay? Therefore this series is convergent by Leibniz test, which is, we can tell, conditionally convergent but not absolutely convergent. Our second example, minus 1 to the power n tan inverse 1 over n. Here an equal to tan inverse 1 over n. What is the graph of tan inverse x? We all of us know, at the point pi over 2 and minus pi over 2, tan inverse x has a asymptote. And this is the graph of tan inverse x, because when x goes to infinity, then tan inverse x goes to pi over 2, and when x goes to minus infinity, then tan inverse x goes to minus pi over 2. So this is the graph of tan inverse x. And here not tan inverse x, here actually tan inverse 1 over n. And 1 over n is goes to 0. Therefore tan inverse half, tan inverse 1/3, tan inverse 1/4, 1/5 would be such type. So since tan inverse 1 over n, therefore an is a decreasing sequence. Okay, and limit n goes to infinity, tan inverse 1 over n. Obviously, since this is n goes to infinity, though, so 1 over n goes to 0. So, and tan inverse 0 is always, this value is 0. So, limit n goes to infinity, tan inverse 1 over n is 0. There, so here the sign would be such type, because this is decreasing sequence, not increasing. And by this graph, tan inverse 1 over n, this sequence is always greater than equal to 0 for all n. Therefore, all condition of Leibniz test also has satisfied here. Therefore, by Leibniz test, we can tell this series is convergent. Now I will see, is this series is absolutely convergent? Here, absolute value of an means tan inverse 1 over n, and that means we have to show, is the series tan inverse 1 over n is convergent or divergent. Here an equal to tan inverse 1 over n. Here actually I will use the limit comparison test, and we all of us know limit x goes to 0, tan inverse x over x equal to 1. For limit comparison test, we have to choose the Bn. Consider Bn equal to 1 over n. Then limit n goes to infinity, tan inverse 1 over n over 1 over n. Since here n goes to infinity and here 1 over n, that means this value and this value would be same, this value equal to 1. And since this value is finite value, therefore here we can use limit comparison test. And by limit comparison test, since our chosen Bn, this series is divergent series, therefore our given series tan inverse 1 over n is divergent. Therefore this series is not absolutely convergent series. Okay, but if we change the series, minus 1 to the power n tan inverse 1 over n square. Similar to before, this is convergent by Leibniz test, but also this is absolutely convergent because here mod n equal to tan inverse 1 over n. Now what would be our chosen bn? Bn would be, sorry, here not tan inverse 1 over n, here tan inverse 1 over n square. Our choosable bn is 1 over n square, and limit n goes to infinity, tan inverse 1 over n square over 1 over n square. This value is also 1, which is finite value. Therefore, by limit comparison test, since the series Bn equal to 1 over n square, this is convergent series. Therefore, by limit comparison test, we can tell the series tan inverse 1 over n square is convergent series. Therefore, this series is convergent by Leibniz test. Also, this series is absolutely convergent series. Okay. Now I will see some example of series which is convergent by limit comparison test. Series n equal to 1 to infinity sin inverse 1 over n square. Here an equal to sin inverse 1 over n square. Then here I will use the limit comparison. That means we have to choose Bn. Consider Bn equal to 1 over n square. Then limit n goes to infinity, sin inverse 1 over n square over 1 over n square. Obviously this value is 1. Since this value is 1, which is finite value, therefore since the series Bn is convergent, therefore sin inverse 1 over n square is convergent. Similarly, we can tell tan inverse 1 over n square is convergent. And there exists a shortcut trick, some shortcut trick. This type of series, sin inverse, here bracket, tan inverse, this type of series would be convergent when the bracket term be convergent. If we consider here n cube, then this series is convergent because this series is our bracket term means 1 over n cube. This series is convergent. But if we consider sin inverse 1 over n, this series does not convergent because here the bracket term not convergent. This is the shortcut trick. Similarly, if we consider 1 over n sin inverse 1 over n, here we can choose Bn equal to 1 over n square. So this type of series also be convergent. But if we consider n equal to 1 to infinity cos inverse 1 over n square, this series does not convergent because when a series convergent, then we all of us know limit n tends to infinity, an equal to 0. Since here an equal to cos inverse 1 over n square, and notice limit n tends to infinity, cos inverse 1 over n square, this is equal to 1. So this series does not converges. Have you understood? Okay. I will say one example which had come in DU exam about series convergency. Notice this series. Obviously, the first series not convergent by limit comparison test. I have seen few minutes ago. Cos 1 over n, limit n goes to infinity, cos 1 over n equal to 1. So this series also not convergent. Similarly, my third minus 1 to the power n e to the power 1 over n. Limit n goes to infinity, e to the power 1 over n, this value is also 1. So this series does not convergent, because if series convergent, then limit of n always tends to 0. Log n to the power log n. In my previous video, when I have seen the Cauchy conditional test, then I have seen this series always convergent. Fifth, sin e to the power minus n. For this, sin x, the graph of sin x always less than x for all x greater than 0. Then sin e to the power minus x less than e to the power minus x. And here the series e to the power minus x means this is actually the geometric series with the ratio 1 over e to the power x. 1 over e. And since we all of us know geometric series is convergent when r is less than 1. Obviously 1 over e less than 1. So this series always convergent, and since this series is convergent, therefore by limit comparison test we can tell this series also convergent series. Okay? Oh well. That means this series also convergent series. Now I will see what is the power series. Power series which is represent as n equal to 0 to infinity Cn x to the power n. If we express, then this would be C0 plus C1x plus C2x square plus C3x cube, so on, which is actually be a function. That means power series represent as a function, and which is look like polynomial, where C0, C1, C2, this is the coefficient of this polynomial. And here the domain of power series is set of those x for which fx converges. Actually, sometimes power series is written as n equal to 0 to infinity Cn times x minus a to the power n, where a be the center of this power series. Actually, power series means here the series represent as function, which is look like polynomial y equal to x square. This is be a polynomial, but if we take here y equal here this graph, then here the center would be different. So a power series actually represent as Cn x minus a to the power n, where a be the center of this power. Now my question, when a power series would be convergence or divergence? Sometime here there would be use ratio test. Now I will see some example. Our first example, series n equal to 0 to infinity n factorial times x to the power n. Here I will use the ratio test. Ratio test is, since here n equal to n factorial, that means here I will use limit n tends to infinity absolute value of n plus 1 over n. Then this value would be n plus 1 factorial over n factorial times x to the power n plus 1 over x to the power n. This value is equal to limit n tends to infinity n plus 1 times x, which is equal to mod x times limit n tends to infinity n plus 1. And this value does not exist if absolute value of x not equal to 0. And this power series exists when only x equal to 0. That means this power series is converges only when x equal to 0, because when x equal to 0, then term of whole series would be 0. Always I will get the finite limit, which is actually 0. So only converges this power series for x equal to 0. Otherwise, the series does not converge for non-zero x. Second example, series x to the power n. Obviously, this is geometric series and this series is convergent when mod x less than 1. Otherwise, this series is divergent. Third example, x to the power n over n factorial. Also, I will use the ratio test. Limit n tends to infinity x to the power n plus 1 over n plus 1 factorial times over x to the power n. And this value would be x over n plus 1 limit n tends to infinity. Just mod x cancel, then this value would be limit n tends to infinity 1 over n plus 1. After putting the limit, this value would be 0, which is less than 1. Therefore, since this value is less than 1, therefore this power series is converges for all x. This power series converges only x equal to 0. This power series converges only mod x less than 1, and this power series is converges for all value of x. Now I will see one new concept about power series, radius of convergence. Power series is actually denoted as n equal to 0 to infinity cn x minus a to the power n, where obviously this a be the center of this power series. For power series convergence, we have seen few minutes ago, there exists three possibilities. Possibility 1, the series converges when x equal to a. Possibility 2, the series converges for all values of x. Possibility 3, for positive real number r, such that absolute value of x minus a less than r, the series convergent. For absolute value of x minus a greater than r, the series divergent. Okay. First possibility, the series converges when x equal to a. Here the radius of convergence is actually 0. Here second possibility, the series converges for all values of x. Here the radius of convergence is infinity. Then one new term, interval of convergence. Next is interval of convergence. Interval of convergence is actually for all value of x for which the series converges. Let's see the picture. Here a be the center of radius of convergence, and here a minus r, here a plus r. For this region, for all values of x, the series converges. Therefore, radius of convergence here r. Without this interval a minus r to a plus r, the series is divergent. Actually, we can think radius of convergence means circle in one dimension. Here center is a with radius r. Now let's come back our previous example. Here I have seen the limiting value is infinity, and this series converges when only x equal to 0. That means for this example, here actually radius of convergence is 0, and interval of convergence is when x equal to 0, then that means interval of convergence is only the point 0. Second example, here radius of convergence is 1. That means interval of convergence is, since center is 0, mod x less than 1. This is the interval of convergence. Third, Here I have seen this series converges for all values of x. For this example, radius of convergence is infinity and interval of convergence is minus infinity to plus infinity. This is the interval of convergence. Now I will see another example. Here the power series x to the power n over n times 2 to the power n. What is the radius of convergence? Radius of convergence means for what value of x this power series is convergence. For this, here I will use the ratio test. Ratio test is n plus 1 over n. That means this is limit n tends to infinity. This would be n plus 1 over n. That means x to the power n plus 1 over n plus 1 times 2 to the power n plus 1 times over n means this would be n 2 to the power n over x to the power 12 over x to the power n. And this value would be limit n tends to infinity n over n plus 1, here absolute value of x over 2. Obviously, this value of the limit is 1. That means this value is mod x over 2. Therefore, radius of convergence of this power series is actually would be for all value of x that who is the series converges. That means this would be less than 1. Therefore, radius of convergence would be 2 and interval of convergence is my open interval minus 2 to 2. For this interval, this power series is converges. I hope my all viewers have understood what is the radius of convergence, what is the interval of convergence. This geometry is elaborately. In my next video, I will discuss this concept elaborately. Actually, power series is very important for complex analysis. If you don't understand the power series, what is the power series, what is the radius of convergence, what is the interval of convergence, then you will never understand complex analysis. What is the actually complex analysis? The base of complex analysis, actually the power series. So, at first I will hardly recommend you, please see today's video with pay attention. And if you have any queries about this video, please do comments in comments box. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.